It is true that HW254 diesel locomotive car wiring, or DLO cable, generally has a higher ampacity rating compared to THHN or THWN under certain conditions. According to Houston Wire's website, HW254 has an ampacity of 65% of copper conductors at 75 degrees Celsius in dry locations. THHN or THWN has an ampacity of 60% of copper conductors at 75 degrees Celsius in dry locations. This means that HW254 can carry a higher current than THHN or THWN of the same size and in the same operating conditions. Article 310.10 requires all conductors to have an ampacity sufficient to carry the maximum load without overheating. Article 310.15 allows ampacities other than those listed in tables 310.16 and 310.17 under two conditions. Firstly, engineering supervision is provided, and secondly, the conductors are tested and found to have the ampacity claimed. Article 310.16 provides the standard ampacity ratings for conductors installed in various conditions and configurations. In the absence of termination ratings for the alternating current drive, Annex B in the National Electrical Code provides a method for determining ampacities other than those specified in tables 310.16 and 310.17 without requiring engineering supervision. Annex B requires the following conditions to be met. Firstly, conductors are not smaller than number 12 American wire gauge copper. Secondly, ampacity is based on actual testing. And thirdly, conductors are used in cables or raceways that are specifically designed to carry the ampacity claimed. DLO cable does have a higher ampacity capacity than THHN or THWN in dry locations. In the absence of termination ratings for the alternating current drive, Annex B in the National Electrical Code could be used to determine the ampacity of HW254 cable used in this application without requiring engineering supervision. Ampacity refers to the current carrying capacity of an electrical conductor, usually expressed in amps. It's the maximum amount of electrical current a conductor can carry continuously under specified conditions without exceeding its temperature rating. Several factors influence a conductor's ampacity. These include, firstly, conductor material. Copper and aluminum are the most common conductor materials, with copper generally having a higher ampacity for the same size conductor due to its lower resistance. Secondly, conductor size. Larger conductors have a greater cross-sectional area, allowing them to carry more current with less resistance and heat generation. Thirdly, insulation type. Different insulation materials have different temperature ratings. Higher temperature rated insulations allow conductors to operate at higher ampacities. Fourthly, ambient temperature. Higher ambient temperatures reduce the conductor's ability to dissipate heat, thus lowering its ampacity. Fifthly, installation method. How a conductor is installed, such as in free air, in a raceway, or buried underground, affects its ability to dissipate heat. Grouping of conductors. When multiple current-carrying conductors are bundled together, their combined heat reduces the ampacity of each conductor. The National Electrical Code provides tables, such as Table 310.16, that list the allowable ampacities for various conductors based on their size, insulation type, and installation conditions. These tables are essential for ensuring that conductors are not overloaded, which can lead to overheating, insulation damage, and fire hazards. Rating factors are applied to the ampacity values in these tables to account for factors such as ambient temperature, the number of conductors in a raceway, and other conditions that can affect heat dissipation. For example, if a conductor is installed in an area with a high ambient temperature, its ampacity must be derated to ensure it does not exceed its temperature rating. Annex B of the National Electrical Code provides additional guidance on ampacity calculations and adjustments for specific conditions. It includes detailed methods for calculating ampacity based on conductor properties, installation methods, and environmental factors. Annex B is often used for more complex or non-standard installations where the standard ampacity tables may not be directly applicable. The ampacity of a conductor is crucial for electrical safety and proper system operation. Overloading conductors can lead to overheating, insulation breakdown, and potentially fires. Ensuring that conductors are properly sized and installed according to the National Electrical Code and other relevant standards is essential for maintaining a safe and reliable electrical system. DLO cable, or diesel locomotive cable, is a flexible single-conductor cable designed for use in diesel electrical locomotives and other heavy-duty applications. It is known for its high ampacity, durability, and resistance to abrasion, oil, and chemicals. DLO cable typically has a stranded copper conductor and is insulated with a thermosetting compound such as ethylene propylene rubber, or EPR, or cross-linked polyethylene, or XLPE. The insulation provides excellent electrical properties and resistance to heat and moisture. DLO cable is commonly used for connecting generators, motors, and other electrical equipment in locomotives, as well as in other industrial applications where high current carrying capacity and flexibility are required. It is also used in power distribution systems, welding equipment, and battery chargers. DLO cable is available in a range of sizes, from number 14 American wire gauge to 2000 kc mil, with ampacities varying depending on the size and temperature rating of the cable. It is typically rated for 2000 volts, making it suitable for use in high voltage applications. DLO cable is designed to withstand harsh environments and is resistant to abrasion, oil, chemicals, and extreme temperatures. It is also flame retardant and meets various industry standards such as those set by the Association of American Railroads, or AR, and the Institute of Electrical and Electronics Engineers, or IEE. When installing DLO cable, it is important to follow the manufacturer's recommendations and all applicable electrical codes and standards. Proper termination techniques and the use of appropriate connectors are essential for ensuring a safe and reliable connection. THHN and THWN are both types of single-conductor building wire commonly used in residential, commercial, and industrial electrical systems. THHN stands for thermoplastic high heat resistant nylon coated, while THWN stands for thermoplastic heat and water resistant nylon coated. THHN and THWN wires are insulated with a tough, abrasion-resistant nylon jacket over a polyvinyl chloride or polyvinyl chloride insulation layer. This construction provides excellent protection against moisture, oil, and chemicals, as well as mechanical damage. THHN and THWN wires are typically used for general-purpose wiring in conduit, cable trays, and other raceways. They are also used for internal wiring of appliances and equipment. THHN and THWN wires are available in a range of sizes, from number 14 American wire gauge to 1000 kc mil, with ampacities varying depending on the size and temperature rating of the wire. They are typically rated for 600 volts, making them suitable for use in most low-voltage applications. THHN wire is rated for a maximum operating temperature of 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations, while THWN wire is rated for a maximum operating temperature of 75 degrees Celsius in both dry and wet locations. When installing THHN and THWN wires, it is important to follow all applicable electrical codes and standards. Proper termination techniques and the use of appropriate connectors are essential for ensuring a safe and reliable connection. The National Electrical Code provides specific requirements for the installation of THHN and THWN wires, including conductor sizing, ampacity dirting, and grounding. It is important to consult the National Electrical Code and other relevant standards to ensure that THHN and THWN wires are installed correctly and safely. Article 310.10 of the National Electrical Code covers the general requirements for conductors, including their ampacity, insulation, and installation. It requires that all conductors be suitable for the voltage, temperature, and environmental conditions in which they are used. Article 310.10 also specifies that conductors must have an ampacity sufficient to carry the maximum load without overheating. This means that conductors must be sized appropriately for the amount of current they will be carrying, taking into account factors such as ambient temperature, the number of conductors in a raceway, and the type of insulation used. In addition to ampacity requirements, Article 310.10 also addresses the insulation of conductors. It requires that conductors be insulated with a material that is suitable for the voltage and temperature to which they will be exposed. The insulation must also be resistant to moisture, chemicals, and other environmental factors that could degrade its performance. Article 310.10 also includes requirements for the installation of conductors. It specifies that conductors must be installed in a manner that protects them from physical damage and prevents them from coming into contact with other conductors or grounded surfaces. This may involve the use of conduit, cable trays, or other types of raceways. Article 310.15 of the National Electrical Code provides requirements for determining the ampacity of conductors. It specifies that the ampacity of a conductor must be determined in accordance with the ampacity tables in Article 310.16, unless otherwise permitted by Article 310.15. Article 310.15 allows for the use of ampacity values other than those listed in the ampacity tables under certain conditions. For example, it allows for the use of engineering supervision to determine the ampacity of conductors in complex or non-standard installations. It also allows for the use of ampacity values based on conductor properties and installation methods, provided that these values are supported by engineering calculations and testing. Article 310.15 also includes requirements for ampacity rating. Ampacity rating is the process of reducing the allowable ampacity of a conductor to account for factors such as ambient temperature, the number of conductors in a raceway, and the type of insulation used. Article 310.15 specifies the conditions under which ampacity rating is required and provides methods for calculating the appropriate rating factors. In addition to ampacity rating, Article 310.15 also addresses the ampacity of conductors in specific applications such as service conductors, feeder conductors, and branch circuit conductors. It provides specific requirements for the sizing and installation of these conductors to ensure that they can safely carry the intended load. Article 310.16 of the National Electrical Code provides the standard ampacity ratings for conductors. It lists the allowable ampacities for various types of conductors based on their size, insulation type, and installation conditions. Article 310.16 includes ampacity tables for copper, aluminum, and copper-clad aluminum conductors. These tables list the allowable ampacities for conductors installed in free air, in raceways, and buried underground. The ampacity values in Article 310.16 are based on the assumption that the conductors are operating at their maximum allowable temperature. The maximum allowable temperature for a conductor depends on the type of insulation used. For example, conductors with thermoplastic insulation such as THHN and THWN are typically rated for a maximum operating temperature of 75 degrees Celsius or 90 degrees Celsius, depending on the specific insulation type. Article 310.16 also includes notes that provide additional information and guidance on the use of the ampacity tables. These notes address topics such as ampacity rating, conductor bundling, and the use of adjustment factors for ambient temperature and other conditions. In addition to the ampacity tables, Article 310.16 also includes requirements for the installation of conductors. It specifies that conductors must be installed in a manner that protects them from physical damage and prevents them from coming into contact with other conductors or grounded surfaces. This may involve the use of conduit, cable trays, or other types of raceways. Annex B of the National Electrical Code provides additional information and guidance on ampacity calculations and adjustments. It includes detailed methods for calculating ampacity based on conductor properties, installation methods, and environmental factors. Annex B is often used for more complex or non-standard installations where the standard ampacity tables in Article 310.16 may not be directly applicable. Annex B includes information on topics such as the calculation of conductor temperature, the determination of ampacity rating factors, and the application of adjustment factors for ambient temperature and other conditions. It also provides guidance on the use of computer modeling and other advanced techniques for ampacity calculations. Annex B is not a mandatory part of the National Electrical Code, but it is a valuable resource for electrical engineers and other professionals who need to perform detailed ampacity calculations. It provides a comprehensive and rigorous approach to ampacity determination that can help ensure the safety and reliability of electrical systems. The selection of the correct cable size and type is a critical aspect of electrical design and installation. It ensures that the electrical system operates safely and efficiently, preventing overheating, voltage drops, and potential hazards. Here are the key steps and considerations involved in cable selection. Firstly, determine the load requirements. Calculate the total current that the cable needs to carry. This involves summing up the currents of all the devices and equipment that will be connected to the cable. Consider future expansion and potential increases in load. Secondly, determine the applicable standards and regulations. Consult the National Electrical Code, or NEC, and any other relevant local or national standards. These codes provide guidelines and requirements for cable sizing, installation, and safety. Thirdly, select the appropriate installation type. Choose an installation type that is suitable for the operating temperature, environmental conditions, and voltage level of the application. Common installation types include THHN, THWN, XHHW, and DLO. Fourthly, calculate the minimum ampacity. Determine the minimum ampacity required for the cable based on the load current and any applicable directing factors. Directing factors are used to account for conditions such as high ambient temperatures, multiple conductors in a raceway, and conduit fill. Fifthly, select the cable size. Choose a cable size that has an ampacity equal to or greater than the calculated minimum ampacity. Refer to the ampacity tables in the National Electrical Code to determine the ampacity of different cable sizes. Sixthly, consider voltage drop. Calculate the voltage drop along the length of the cable to ensure that it is within acceptable limits. Excessive voltage drop can cause equipment to malfunction and reduce overall system efficiency. Use voltage drop calculators or formulas to determine the voltage drop for the selected cable size and length. Seventhly, select the cable type. Choose a cable type that is suitable for the installation environment and application. Consider factors such as flexibility, resistance to abrasion, moisture, chemicals, and sunlight. Common cable types include single conductor wires, multi-conductor cables, armored cables, and underground cables. Eighthly, select the appropriate connectors and terminations. Choose connectors and terminations that are compatible with the cable type and size. Ensure that the connectors are properly rated for the voltage and current levels of the application. Ninthly, verify compliance with codes and standards. Double-check that the selected cable size and type comply with all applicable codes and standards. This includes verifying that the cable is listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or all. Tenthly, document the cable selection process. Keep a record of the cable selection process, including the load calculations, ampacity calculations, voltage drop calculations, and the codes and standards used. This documentation can be helpful for future reference and troubleshooting. By following these steps and considering all relevant factors, you can select the correct cable size and type for your electrical application, ensuring a safe and reliable electrical system.